Can start? Okay, so welcome everyone. This is the lab session of the error mitigation part of this school. And so this morning we had a nice presentation of error mitigation and how Mythic works, how you can mitigate errors using this library that is called Mythic. And now we try to use it really with your laptop. Possibly we will try to install the package, install whatever we need, like Qiskit and Mythic and all the things that we need to run real simulations at this stage, not real hardware, but we will try to mitigate errors using, in particular, the technique known as zero noise extrapolation. So the first question that I have is, do you have a Jupyter notebook environment? Do you know what is Jupyter notebooks? And so who has Jupyter notebook in the laptop? Me? Okay. If you don't have it, you can try to download it quickly, or we have a link later to some online simulated environment in which you can still try to run this notebook. But if you have it, the idea is to do it locally such that you like simulate your real usage of a Python package on your machine. That's in principle how people use Mythic. So we'll try to do all the steps. And the first thing that we need to do, if you have this Jupyter environment, if you know how to use Jupyter notebooks, is to download a notebook that you can find at this link. It's bit.ly 3pzj and little l. This is classical communication channel. Oh. Is it working? Yeah, if you have problems with the link, and for the people in the Zoom chat, in the Zoom call, the link is in the chat. And when you are at this link, I think, let's see what you should get. Okay, you should get this. And there is this button, which is download zip. If you press it, you should get the file. It's a zip file you have to extract. It's just a single file inside the zip file. That's boring, but it's there. It's called Mythic. And when you have the file, you have to open a Jupyter notebook. And from the Jupyter notebook environment, you have to find the file and open it. Take your time, because that's important, and we can wait. And the notebook is not very long, so we can take all the time that we need to set up everything and don't lose people. I see that there is something in the chat, maybe. Ah, that's me. Okay. And meanwhile, and the next step will be to install Mythic. You can do this with pip install Mythic. And you can do it in a terminal. It's better probably, but you can also do it in the notebook itself. You can just remove, in the first code cell, there is this. Oh no, that's the live one. Okay, let's go here. This cell here, you remove the comment and execute the cell. This will install Mythic. And if you don't have Qiskit, you can remove this comment and also execute the second cell, and it will install Qiskit. You can do this here, or you can do it in a terminal, whatever is more familiar for you. And these are the only two non-standard packages that we are going to need. And I hope you don't get errors when you install the things. If you get errors and you are blocked, you don't know what to do, there is this link here, which is a My Bander link that will open a kind of virtual online Jupyter environment in which you can try to upload the previous file. But I would not suggest this as a first option. The best thing is to make everything working in your laptop. And if you have any problem, please ask. I can work there. Also, Misty and Nate and Nathan are here. They can help you with everything. Going? Who managed to have first to open the notebook with Jupyter? Raise your hands. Okay. No. Second question is, who managed to install Mythic and Qiskit? Work in progress. On the Qiskit side or on the Mythic side? Yeah, that could be due to the Python version. So this is, if you manage to create an environment with Python 3.8, if you use Anaconda, for example, you can do it. It's better 3.7 or 3.8. That's another option, yeah. You have errors even in Collab? Okay, yeah. As long as it goes down, it's okay. Small warnings are okay. And yeah, I know we know that this can take a bit of time, but we really want to reproduce what you will do at home. So, and we want to help with these steps. And maybe a quick overview before I start executing things is how ZNE works in Mythic. We have seen this morning how it works in general, but just this diagram is already enough to know what we are going to do. So Mythic takes a quantum circuit, which is a quantum program, and compile the circuit into a set of auxiliary circuits of different depths. And these circuits will be more sensitive to noise in different ways. And so when we execute them on the hardware to compute expectation values, we will get expectation values at different noise levels. And so we can extrapolate to the zero noise limit. That's what is going on behind the scenes. But I think if we are ready, we can start going through the notebook. I think, yeah, Nate is helping there. If you still have, if there is someone who still has problem installing things, you can ask for help maybe by Misty or Nate. Okay, it's takes time, right? Okay. Huh? Oh. In Anaconda, there is not NumPy, it's strange. Yeah, that's the problem.
You want to do on Python 3.8?
If you have it, it will be weird.
Yeah,
That's it's a recent problem with these new Python things. So I will write it here. So if you did, for those who did all the steps, you can try if your installation is fine by executing the first cell here. Here it gives to me 0.18, but you should get maybe 0.17. It's fine, and something for the Qiskit version 2. You should get. If you can choose the 0.36.2, it's better. If you have another one, it should probably work, but you know, things tends to be tricky. And if you still have big problems, there is this link here, and you can try using this. So it's this virtual binder environment that you can use. And you can do it also in parallel. You can just open this and see how it goes in this way. You can go to the link, I think, to this link that you see here, because yeah, you have to do copy and paste or just upload the notebook. It's a bit more complex, but if you need to install anything like even Python from scratch, it will take time. So maybe, yeah, if some has problems, could go near Nate and use the laptop of Nate, for example, or yeah, you can go close to Nathan and use the notebook of Nathan. That's a don't be shy. If you still have problems, that's an important phase of the lab. So if you have it working, we can go on. Who has it working? Raise your hands. Okay. Okay. Most of the people. Maybe we can go on, right? If you still have problems, there is still this link as a backup option. If you can still open it in the background and use it as a second option, and it's always better than nothing. So another page that you could open and can help you during the lab is the documentation. This is it, mythic.readthedocs.io. This will give you the user guide here, and also all the API docs. So all the docs for all the functions of Mythic. It can be useful during the lab. There will be also links in the notebook to the docs, and so there will be some help from this documentation. Nate, what's the situation up there? More or less, going. Okay, because I think what about if you just share your laptop and then afterwards you can continue installing things, right? But it's fine to use another laptop or the laptop of your neighbor and just follow the discussion, because I think it's important now to everyone to follow the discussion here, and you can continue installing afterwards, okay? If you have a, yeah, exactly. The first thing that we want to do is to generate a circuit that prepares a GHZ state for a number of qubits, and I suggest using 7 qubits because later we are going to use a device, a fake device with 7 qubits. And you can do, if you know how to generate a circuit that prepares a GHZ state, you can do it manually, or you can use the Mythic utilities that are in mythic.benchmarks. There is a function which is called generate GHZ circuit, and you can just execute this. So this will automatically create the circuit that prepares this state. Otherwise, if you're using Qiskit, you could just write down whatever circuit you want. But in this demonstration, it's better to use the same circuit. So it's an Hadamard followed by control node, and we'll create this superposition of 0, 0, 0 and 1, 1, 1. So that's the ideal state that we want to prepare and maybe to measure in a quantum computer. That's just an example. And then the question is, what is the observable that we want to measure? Because error mitigation works and it's well defined each time you want to compute an expectation value of something, of an observable. And a very simple observable that we can define in this case is this projector on the 0, 0, 0, 0 state and 1, 1, 1, 1 state. Basically, measuring the expectation value of this corresponds to measure what's the probability of getting the 0, 0, 0 state plus the probability of getting the 1, 1, 1 state. And for the ideal GHZ state, this is 1 by construction. So we know that the ideal expectation value is 1. If you have noise, you will get a different number, actually a smaller number, because the maximum that you can get for this operator is 1, and so you will get a reduced number of, a reduced value of the expectation value. And so the first thing to do now is to just check this fact. So if you have an ideal quantum computer, the ideal expectation value is 1. If you have noise, it's different from 1. And to do this, you can follow basically the structure that you see here. You can import all these Qiskit things, and you can initialize an ideal backend, which is a Qiskit simulator, ideal. You can append measurements here, and now you have to run these circuits and to extract all the counts. Each time you do an experiment on a quantum computer, you get counts. And if you don't know how to do this, you can follow this link. This is a Qiskit example in which an ideal simulator is used to exactly measure a GHZ state. It's a smaller one, 3-qubit one, but it's the same thing, on an ideal simulator and on a noisy device. And you can do exactly the same things on this notebook. Basically, you have to fill each time you see this comment to do run circuit or to do something, you have to put some parts of the code here. And a similar thing for the real simulator. And then you need to extract the expectation value. But let's do it step by step. So what we need to put here is something like job, ideal backend, circuit to run, the number of shots that we initialized in the previous cell. And once you have the job that is executed, you could extract the counts. If you are familiar with Qiskit, it should be something like job, result, get counts. Let's see if it works. Okay, you have to execute all the previous things. Yes. Please. Yes, .run. Okay. That's the ideal simulation of a measurement for a GHZ state. More or less 50% of the times you get the bit string 00 and 50% 1111. So what happens if you have noise? So to simulate noise, we initialize a backend, which is a fake version of a real QPU. You can do this with Qiskit. You have these mock devices. In this case, we use fake Jakarta. And we also compile the circuit into the native gates of Jakarta. That's what this cell is doing. And now we need to do the same. Basically, we use this noisy device to run the circuit to run, and we extract the noisy counts. Equal job result get counts. No. Interesting. Okay. That's noisy job, right? Okay, here, the ideal one. So in this part of the notebook, we are just reproducing what you will do with Qiskit if you want to run a circuit. We are not using Mythic. We are not mitigating errors at this point. We are just running a circuit on an ideal simulator and later on a noisy simulator. We want to check the impact of noise. So that's the ideal part. Basically, the only thing that you need to change is if using the ideal backend or the noisy backend when you run the circuit. The structure is the same. And what you should get if everything works is an histogram like this, which you get more or less 50% of the times the 000 string, 50% the 111 string, and also some random counts for other bit strings because you have noise. And so sometimes you get even unexpected results that are not even in the support of the ideal state. So this is what you get in principle, in practice, on when you run things on real hardware. And
excuse me, Professor.
Yes.
Could you please tell us which type of noise is there and what is the main source of the noise?
Yeah, so basically when you initialize this fake Jakarta device, it's a complex noise model that should more or less reproduce all the errors that you have on the hardware. Of course, it's not a perfect emulator of the hardware. And usually you have measurement noise, decoherence noise, amplitude damping noise, and all these things associated to all the gates of the circuit. And basically, this noisy backend object takes care of emulating the effect of noise. We are not assuming a specific and artificial noise model, but it's what IBM provides, basically.
Ah, okay, thank you.
You could even simulate an artificial noise model, a theoretical one, but we try to be as close to the hardware as possible in this notebook. Did you get the both histograms? More or less? Okay. Good. And once we have the counts, we still need to compute the expectation value, right? We need to compute the expectation value of this operator that we use as a kind of example of an observable. And by definition, basically, the expectation value of this is the probability of the 00 string plus the probability of the 111 string. And so we can estimate this from the counts. So the expectation value should be something like ideal, counts. This is a dictionary of all the possible bit strings. Should be like 7 zeros, 1, 2, 3, 4, 5, 6, 7, plus the same thing, 1, 2, 3, 4, 5, 6, 7. These are the number of counts that we obtain for 0, 0, 0, 0, and 1, 1, 1, 1, 1. And this should be normalized by the number of shots. This is how you would compute an expectation value when you use a quantum computer. This simple expectation value, right? Let's see if it makes sense. Yes? Yeah. I can wait. Yeah. So to get the ideal counts, you need to add these two lines on the existing cell, which is you first need to run a job, ideal backend dot run circuit to run shots equal shots. And then the ideal counts can be extracted with job dot result dot get counts. Because that result will always be 1, right? if you take two numbers and you divide by the sum, you take the sum of these two counts, how many times I got the 0, 0, 0 string? Yeah, no, actually that's, so 0.5 is a probability. So it's like the number of times that you get it divided by the number of measurements. What you see in the histogram is already normalized. If you take basically these two numbers, 0. And you sum, it works, but basically this function plot histogram is automatically normalizing it. If you want to extract these two numbers, you need to take the counts and normalize. It's a, so this function plot histogram is a bit complex. It's it does already all this post-processing automatically. Exactly, that's the idea.
Excuse me, I have another question. Based on the theory, before applying the noise, the probability for 0 and 1 should be half and half.
Excuse me, people in the room, can you talk slowly because I don't.
Yeah, before applying the noise, the probability for 0 and 1 should be half on half. But there it is 0. Yeah, there is difference between them, 2%, 0.2%. So
good question. So this type of error is due to the statistical error that you always have in a quantum computer, even if it is perfect, because you run a finite number of measurements that are probabilistic anyway, even in a perfect quantum computer. And so when you do these measurements and you normalize, you get numbers that are that have some statistical fluctuations. If you take an infinite number of measurements, you will get exactly 0.5, 0.5. Since the number of measurements is finite, you always get some error. But this type of error is statistical. It's not due to the error in the hardware.
Okay, thank you.
Good. Good. Any question up to here? Is it clear what we are doing here? We are just trying to estimate the expectation value of this operator, which is by construction the sum of two probabilities, and we are estimating the probabilities as the sum of two frequencies. And as you can see, the ideal expectation value is 1, and since you have noise, the noisy expectation value is not 1. That's the error due to the hardware device, hardware noise. It's not statistical, it's just purely due to the errors of the backend. And the idea of Mythic and error mitigation in general is to try to get a better estimate of this ideal value, which is 1. Can we do something such that instead of getting 0.8, we get something larger, something closer to the ideal result? And here is where Mythic comes into play. And yeah, maybe we are ready to go to the next step, which is applying zero noise extrapolation with Mythic. And the way in which Mythic is designed is in such a way that in principle, if you are able to run things on a front end like Qiskit, Cirq, PyQuil, using Mythic should be just a minor change in your code. So let's see how it works. The only difference and the only important thing that you have to remember if you want to use Mythic is the concept of an executor. So a function that takes a circuit, run it, and produces an expectation value as a final result. That's the simplest model of an executor. We have more complex executors in Mythic, but let's focus on this. Let's try to write a function that we call execute that just does the previous things that we already did, but wrapped into a function. So this should take the same compiled circuit that we defined before, this here. Actually, yeah, here I should put the compiled circuit, but the result seems to be the same. So sorry if I confused this, but we just executed the circuit to run, but the correct way will be to execute the compiled circuit, right? For the noisy case, but the result seems to be the same anyway. Okay. Because basically each noisy backend has different gates, and so it is a good practice to first transpile your circuit into the gate set of the noisy device, such that you get a new circuit which is compatible with the hardware. Transpile, it's like compiling. You take your circuit, which is the circuit that we defined before, the GHZ circuit. It has some gates that maybe are not present in the hardware gate set, the real things that the hardware is able to run. And so those gates are decomposed into other gates that the hardware is able to run. So to see this, let's just print. Like this is the GHZ circuit that we defined before with measurements. Let's see how it looks, this compiled circuit. You see, it's a bit more complex because it's under this, there is a mapping of the inputs qubits to the hardware qubits, reshuffling of the qubits, decomposition of the Hadamard gate, and more or less that's it. But you see all these chain of C0 are probably swap gates. I'm not sure what's going on here, but yeah. But this is something that Qiskit is doing for us, so let's forget about this problem and go on with the rest. So this was already written here, so it should work for everyone. This cell was present in the notebook. If you just run it, it compiles. And if you put this compiled circuit into the noisy backend.run compiled circuit, you should get the noisy job, noisy counts, histogram. That's the same thing as before. So how many of you got this ideal expectation value 1, noisy expectation value 0.7 something? Good, good. Okay, now that looks, maybe sometimes it's good to restart the notebook. Maybe there are some. Can you repeat this?
Pushing the compiled circuit into the same thing as before, where we say use backend dot run.
Again.
Are we not applying? Are we not applying the backend twice?
No. As you can see here, this line is just a compilation and maps the input circuit to a compiled circuit. And when you do noisy backend run, if this is already compiled into the good gate set of the device, it's not compiled again. Print compile circuit like this. Yeah, it's very involved. It's less easy to understand when you look at this, but it's the same unitary, but compiled in a different way and applied to different qubit orderings, but that's the idea.
Sorry,
yeah.
The noise population with expectation value 0.008 is very low.
It's very low, yes. Let me see. The histogram looks good, right?
Yeah, the histogram.
Maybe it's just the way in which
I'm not sure it's on the correct.
Can you rerun these, and this?
So this
Oh, it takes time. This is Bander? Okay, good. And then go down. Noisy qubits, noisy counts. Yeah, you should work. Ah, I know. Can you go up? So when you do the run function, you should put the shots. You are using the default number of shots and not the, okay. Yes. No, I don't. Is there? No, I think it's my message that it's appearing there. Okay, we had a question from a student here that there was a problem with the normalization, and be careful of putting this option here, the number of shots when you run the circuits. Otherwise, Qiskit assumes a default number. I don't know how much it is, but when you normalize later, you get strange results. So, okay. Good. I think we can go on and try to mitigate this type of error. What we need to do, as I said before, we need to write a function that takes a circuit and reproduces this number, this expectation value. Basically, we just need to copy what we did before, noisy job equal noisy backend.run and so on, the counts. Yes? We can fix it to this global variable that is written here, or it could be an argument of that function. But if it is an argument, it's better to use a default value, because it is important for Mythic that this function just takes as a unique required argument, which is the circuit. And the other should be default optional. Yes. Yeah. I don't know. Yeah. So is the question why this result looks in this way and not in another way? So the exact backend doesn't need a compilation. So the question is why the compilation depends on the backend. And so I think one of the question is why, when I compile the circuit, I need to specify a backend. Okay.
No, but that's not that's yeah, the noise of the cat. Yeah. That's
these are the native gates of the Jakarta device. Yeah, the real ones for sure. Okay, I think we need to go on, otherwise we... Let's see if there is something that we can fix. So I think the checkpoint is this one. If you got these two numbers, more or less, up to statistical error, we can go on. Good. Let's try to go on. So this function, execute, is a function that should take a circuit and just produce a noisy expectation value. So what we need to do is to go back and see exactly the steps that we did to compute the noisy expectation value. So what we did, we just run the circuit on the noisy backend, get the job, extract the noisy counts. Let's copy those extractions in the function, like this. And then another thing that we did is, given the noisy counts, we extracted the noisy expectation value using this formula. So we put it here. And then if this function works, should just split out this number. Let's see if it's true. Okay, we just did the same, but using this function. And another thing that you can notice that here, I already coded this print line that tells you it's like a log message. I'm executing a circuit of depth 18. That's the depth of the circuit that it's executed. This will be helpful later to understand how Mythic is calling this function. You will see a lot of these messages, and you know how many times this function is called by Mythic and so on. But up to now, we did just nothing. We just wrapped the previous code into a function. Make sense? Okay, that's fine. Maybe that's how the compilation, there is some randomness in the compilation. In the transpilation, that this instruction is not deterministic. This one, where it is? This. There is some randomness in each time you call this function. And I guess so. Sometimes, because it's like you take a random combination of qubits, you see how long it is. There is some, you can actually, if I'm not wrong, you can put a seed on this function to get deterministic things, but.
The number of gates, the number of the depth of the system is the effect of the noise, not this simulation of the noise.
No, yeah, the depth is just a property of the circuit. If you get a number, yeah, maybe the transpiler compiled your circuit with a gate less. It depends on how it decomposed the input circuit into the native gate set. And since there are many ways, equivalent ways of doing it, you get some fluctuations. Yeah. And yeah, maybe yeah. You can try again to re-execute all the cells, and you should get similar results, but slightly different. Okay, so up to now we did nothing. Now we are ready to use Mythic. The idea is that what Mythic wants to know in order to apply zero noise extrapolation in the minimum situation is just knowing the circuit that you want to mitigate, knowing this function that executes circuits. And the rest are just optional, additional advanced options. But this is the minimum thing that we need to pass to Mythic. So assume that we want to do zero noise extrapolation. The first thing that you need to do is to import from Mythic the ZNE module. That's the zero noise extrapolation module. And in this module, there is a function which is ZNE.execute with ZNE. And the documentation of this function is given at this link. So what you need to do now is to copy this link, open it in your browser, and try to just checking the documentation, but actually it's very simple. You have to understand what should be put as a circuit and what should be put as an executor. I basically already told you more or less, but I give you like a few minutes to just understand how this function works, and hopefully you will get an error mitigated result. And yeah, if you have questions on the chat, you can write in the chat. So according to you, what should I write here? Circuit equal compile circuit. That's the circuit that we want to error mitigate, right? Is the GHZ circuit compiled to the noisy backend. What should I put here? Execute. Perfect. So let's see if it works. So if thing works, you should see a result like this. Like you will see 3 times this log message that is inside this function, executing a circuit of depth something, executing a circuit of depth a larger number, even larger number, and then that's the final result that you get. This number will be different because of this randomness in the compilation. But more or less, that's the idea. Let me, yeah. Okay, let's go on like this. Let's see how it goes. I usually got a better number. There is some randomness in this compilation step, so each time you run this, you get different things.
Excuse me, Professor.
Yes?
I don't know, maybe by increasing the number of circuit of depths, that expectation value increased.
It should decrease.
It should decrease.
For each of these circuits, it should decrease and decrease more, but then the extrapolation should estimate a zero noise limit, which should be closer to the ideal limit, and so closer to 1. So this number in principle should increase, but the individual noisy expectation values will decay. We will see later what is happening behind the scenes, but yes.
Okay. How about the increasing the number of qubits? Here we have 7. For example,
that's another idea, but that's a different circuit, right? You are changing completely the circuit. Here we are changing the depth.
Oh, okay.
Same unitary, more noisy.
Okay, got it. Thank you.
Good. Did you go to this point? As you can see, it's a bit larger. Actually, we are not mitigating a lot. That's how it works in real life. Sometimes it works good. Sometimes you have less good results. It depends also on the size of the circuit and things like this. Actually, for small circuits, the large part of the noise is measurement errors. These are not mitigated by zero noise extrapolation. And so let's see, maybe with advanced options, if we get better, something better, and how it goes. So you can print the error. As you can see, slightly reduced by Mythic. This just default ZNE case. And let's see what we get with more advanced functions, maybe. And that's the topic of the next section. But before I go on, let's see if you have questions on this, or if you have problems on this. Yes. What's the error, sir? Oh, I don't know. So is the rest before this cell working fine? Of Python? Of Qiskit? That could be strange. Because if the rest is working fine, okay. It could be a Qiskit version problem, yeah.
The default version of Extrapolate, can we start scale noise?
Noise scale parameters?
Yeah.
Let me check. Full output True? No. It's an option. It's a you can do it in the next section. We show how to visualize the expectation values and everything by using factories. Basically, the factory is mutated by the function, and you can extract the numbers.
But again, for example, the third one, 49,
yeah, that's also something that you can try. Yes. For example, you can put here a print statement in which you print the noisy expectation values. You also have this information, but yes, there is a question there. These are the default one, 1, 2, and 3. No. So we are going to explain what is a factor. Factor is an object that determines how you do the extrapolation. So you choose the noise scale factors, even the way in which you extrapolate, if you fit an exponential, if you fit a line, if you fit a polynomial. And there are many ways of doing the extrapolation, and that's encapsulated into a factory object. So it's not just the numbers of the scale factors.
There is a question. The user from online said that they tried to fake Vigo as a backend because
fake Jakarta is not present in your version of Qiskit.
But fake Vigo, I don't know how many qubits it has.
Yeah, it has many. It has less qubits, probably. Yeah, maybe they used a smaller circuit, probably. And bugs in the GNI. You could decrease the number of qubits. But it seems that they arrived to the Mythic cell, so maybe they did it, but they get other errors, maybe from Mythic. I don't know. If you put the error message in the chat, we could help, but I'm not sure what's going on. Sometimes it can be worse. So error mitigation is it's not the ideal error correction that always works. It's a very practical and non-rigorous way of correcting errors. So under some assumptions, you can give rigorous statements, like if the noise is weak, you are doing like first order correction exactly on the errors, but you are not sure what's the second order corrections and so on. There are methods which are more rigorous, like probabilistic error cancellation, but they are more difficult to implement. And so this is the easiest method at all. It can happen that if you try to use it in an algorithm, you get worse result because of this. So, and so hopefully, on average, it works. The improvement is larger than the problems, but so I think we should go on. We have, I think, 15 minutes. It's better to see at least this second section about options. And basically, this second section is a way to explicitly define what's the noise scaling method that we want to use. There are different ways. You could scale the full circuit. You could scale individual gates. And the folding method, there are already in Mythic several folding functions that you can find in the GNI.scaling module. The most important ones are fold global and fold gates at random. You can test both functions if you wish. That's the function that you can try now, like fault global. And the inference method is initialized as a ZNE.inference.a object. That's here, for example, let me be more explicit here. When you do inference.something, you have many suggestions like adaptive factory, exp factory is one, or linear factory for doing linear extrapolation and so on. You can find all this information in the documentation, but in this case, let's assume that we want to do Richardson extrapolation. And so we have initialize a Richardson factory, but the extrapolation also depends on how much you want to scale the noise. This is the scale factors of options. So scale factors equal 1, 2, 3, for example. You could use different numbers and you can check what comes out. These are the most common ones. And to do these two options, I can do it right now. You can see the docs, but I think for the sake of time, it's better if I just do it live now. You can just pass these two objects to the function as arguments and see what you get at the output. So scale noise is the way in which you scale the noise. So we pass the folding function. And the other option is the factory. And so we pass this factory function here. Okay. With these two arguments, you are asking Mythic to use this noise scaling method and this extrapolation method. Let's see if it works. Okay, it works, and actually we got a better result than the previous default method. And the reason why we got this better result, the only difference is the way in which noise is scaled. The default method is fold gates at random. That's the one, the noise scaling method that Mythic is using by default. This should give a result that is less good. Well, actually, it's there is some randomness here, I guess. Because you can see that's exactly the same. Yeah, each time there is a statistical error or two involved. So let's see if I run it twice, what's going on. Yeah, there is statistical errors due to the finite number of shots, but still, you can, on average, yeah, I'm not sure. It really depends on the circuits and on the problem. So maybe here, yeah, you can try to see what happens if I use exp factory. Probably you need more expectation values, like 3, no, more scale factors, 3, 4, 5, 6. You see, more circuits are executed at different scale factors, and an exponential fit is used. Now, that's not a polynomial. You see that there is just a fit. It doesn't look exponential because we are using scale factors that are too small, maybe 15. Let's see if we see an exponential shape. Yeah, more or less. It's more. Yes? A small amount. Yeah. Yeah. So you could try to enforce like extrapolations to always cap, to only clip to 1, but in principle, the aim of zero noise extrapolation is to get an expectation value which is closer to the ideal value, independently if it's a physical or non-physical result. You want a better estimate of that number. Maybe there are more advanced ways of doing this, getting physical results, but that's another problem.
What about like data points that are far
From the fit, it's possible.
not from the fit. Yeah, I mean the fit then the fit is like a decreasing curve.
Yeah, you can try to put more noise scale factors here, like here, noise scale factors 1, 2, 3, 4, 5. Otherwise, there could be an error in the way in which you define the function. Right? No. By the way, yeah, I always use integer numbers here, but they could be 15.3. And what Mythic does is it tries to scale the number of gates such that more or less the number is 15.3 times more the input number of gates. There are also options for doing this, like I think we don't have time to go into these more advanced options, but it's on the documentation. You could set a fidelity for each gate, and if you set that the fidelity is 1, those gates are not folded, are not scaled. Only maybe we can check later what. Are you using the compile circuit? Yeah. So maybe the quick thing that you can try is this function the same that you use? Like noisy job, noisy backend, run, compile circuits, shots. Do you have the shots option? Yeah, I have no idea. We can look later. It's an interesting effect. Okay, I think we just have 5 minutes in principle, right? Yes. So let's try to see how noise scaling is applied by Mythic. So what does it mean to scale the noise of a circuit? How can you increase the depth of a circuit, keeping the same unitary with Mythic? Basically, what does it mean to use fault global or fault gates at random when you do this zero noise extrapolation process? And this is the topic of the next section, which is very simple. So we take a circuit. Actually, now we could take the original circuit variable that we defined before. So let me print it here. So you should have a variable which is called circuit, which is the GHZ circuit. Print circuit. This one, right? We defined this before. If you don't have in the memory, just re-execute the previous cells and you get it. And now let's see how this function, ZNE scaling for gates at random, acts on this circuit. You can see the documentation again of this function at this link. It's very simple. This function takes as input a circuit and a scale factor. Even without using the documentation, you can try to just apply this function and see what happens to the result. Since we have 2 minutes, I'll do it live. Basically, you apply this function ZNE dot scaling dot fold gates at random, and you pass the scale factor argument. You can put 3, which is the simplest scale factor. You will see later why, and see what happens. So what we got is a copy of this circuit, but each gate now is repeated 3 times. And actually, if you didn't have those simple gates, what's going on here is like gate, inverse of the gate, 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 inverse of the gate, gate, and so on. So by construction, this is equivalent to the previous unitary, but it's longer. And indeed, it's longer by a factor of 3, because each gate is repeated 3 times. So what happens if you put 2 instead of 3? What happens is that this is applied to a random subset of the gates. The same trick is applied to this control node, to this, not to this, not to this gate, not to this gate, and not to this gate. And on average, if you repeat this many times, you scale the depth by a factor of 2, and you scale the noise by a factor of 2. Yes?
Can I ask why you ever want to do it locally rather than
Yeah, you could put here 3.5, 14. Yeah, so the question is why I'm always using integer numbers.
What's the benefit? Because if you want to know essentially for the whole circuit what it should always be better to do it globally, since it's just essentially different prices globally, but globally you don't know which parts are going to be more than others.
Okay, so the question is why one should use local folding and not global folding, right? And I think there are two reasons for using one or the other. A reason for using local folding, a good advantage is that you can use scale factors that are not multiples or that are not odd integers. Like if I use even a scale factor of 2, as you can see, there is some randomness. And on average, you sample all the circuit. If you use global folding, you fold only a final part of the circuit, which is not very nice. And other reasons is in this way, yeah, maybe there is not a clear, rigorous theory that tells you one method is better than the other in general. What we noticed is that with the time correlations in the noise, global folding is better. But if the noise is Markovian, it's not so clear which one is the winner. You increase the noise, yeah. But even with, so the question is, not the question, the comment is, if you use global folding, you can say that you increase the noise by the data processing inequality, because you apply the channel again, the inverse of the channel again, so there is a data processing. For sure, you introduce noise. But even here in local folding, you apply a local channel inverse. It's a local noise. You are scaling the local noise, and the global channel, you are scaling the global noise. And I guess that there is not a clear answer which one is better, because yeah, things can go very unexpectedly. Like if the global circuit, for example, is damping into the ground state because of some amplitude damping noise, maybe you are not able to undo the process with the full unitary, the full inverse of the unitary and the unit. So it's an open question. Nobody knows what's better. We are testing on hardware both and see how it goes. So basically, if you now apply the fault global function, yes?
Also, maybe local folding to some extent was the first to be proposed.
It was one of the first techniques that have been proposed in the literature, and actually global folding was something that we more or less introduced with Mythic and seems to be quite good in some cases, but we don't claim that it's better than other methods and so on. By the way, this local folding looks very similar to the pulse stretching technique, which is one of the original ways in which noise has been amplified in the IBM original proposal. So you are simulating a slow evolution of the circuit. This global folding, if you plot it, yes. Oh. Oh, how many errors I'm applying? Okay. You see, that's the global circuit, that's the inverse, that's the global circuit again. And that's the structure, and it doesn't look as slow as a pulse stretching technique. It's not a slow execution of the same unitary, but it looks like a time reversal. You do the computation, you undo the full computation, you redo the computation again. It's a kind of time reversal of the Hamiltonian. But more or less, you still scale the number of gates, and more or less they work in a similar way. I think that's all. I'm not sure if I should go on because I already went too much over, right? I will share later, maybe now, the link to the notebooks and to the solution. There is also a full notebook which just works. We don't have to. Do you think I can go on? It's just two code cells. Maybe we can try to go on. So what we are doing here, we have seen how folding works. We can do basically zero noise extrapolation in a more manual way, in a more low level way. So what we do, first we decide the scale factors, 1, 2, 3, for example. And instead of calling this function execute with ZNE that does everything for you and you don't see what's going on, especially if you are a researcher, you want to understand what's going on, the idea is let's do it manually. So let's take the compiled circuit and manually apply these folding functions with different scale factors. So this line just creates a list of noise scale circuits of different depths. Okay, that's just compilation basically. Do you have questions on this? Okay. Now, we just need to compute expectation values for different circuits that we scaled. That's how we compute basically where it is. Those points, right? Expectation value at different noise levels. Since we have already defined this function that takes a circuit and produces a noise expectation value, we just call this function for all the circuits that you have in the previous list. Okay, we get these numbers, and if we print them, that's what we get. A list of 3 numbers, which should be decaying, and indeed they are decaying, 0.79, 73, 71. We are basically trying to compute this number, this number, this number for scale factors 1, 2, 3, but in a manual way. And when you have this, there is still the second step, which is the inference. Now we have data. We still need to extrapolate to the zero noise limit, and we have a lot of freedom also in this phase. For example, let's try to do Richardson extrapolation, the same thing that the function was doing automatically. What you need to do, you just initialize a Richardson factory object. You upload your data that you computed. So you put the data into the factory object. There is a push method for doing this. Basically, you tell the object that at scale factor S, you got this expectation value. At phase factor S1, you get this other expectation value and so on. So now the factory object has all the information, all the data. And if you call the factory.reduce method, this gives you the zero noise limit. And also, if you call other methods after this, like polyfit or other methods, you can extract more information as we did before, like the fit, you can know how the extrapolation went and so on. Basically, we just did what we did before, but step by step. And the advantage of doing step by step is that now we can take the same data that in principle we measured on the hardware. Maybe this was expensive, maybe we paid money for this. And we don't want to execute again the circuit just to do a linear fit instead of a polynomial fit or an exponential fit. We just take the data and we push them into a different factory object to get a different extrapolation. So in this case, it is suggested to use a linear extrapolation. Let's try. So ZNE inference dot linear factory, scale factors, and the rest is just the same. Let's see what's going on. So as you can see, let me reduce the zoom here. These data points are exactly the same data points that you see here. So same data, same noise scale factors. I'm just changing the way in which I do the extrapolation. I assume a linear dependence instead of a polynomial dependence. And that's how you can basically test different extrapolation methods with the same experimental data. And this was the last section of the notebook. I think if you manage to work on this, basically you know how to use zero noise extrapolation with Mythic. There are a bit more advanced options, but this is really all you need to know to just use Mythic in your computations. Remember these basically two things. First, execute your circuits on your hardware, backend and front end. You should get a noisy result that maybe it's not equal to the ideal one. Then put the code that you have already used into an execute function. That's really the only thing that you need to remember. Wrap your code that takes a circuit and produces an expectation value into a function. Once you have done this, using Mythic should be very easy. That's the core message of this notebook. And yeah, if you have other questions, I'm here. Otherwise, I think we can close it here. And we are here. You can ask questions also later. And I hope it was useful for you to understand how to use Mythic. Good. Thank you.